This conference will now be recorded.
Hello everyone, we'll start with a problem and then there will be two more laws of combination, which is reciprocal and multiple, and after that there will be Avogadro's law, and then some related problems, and also Dalton's atomic theory and its limitations. So here the problem is saying that 0.36 gram of magnesium is reacting with chlorine, and it is producing 1.44 gram of MgCl2, that is magnesium chloride. So this is one method by which MgCl2 is produced. So we can say Mg plus chlorine, we are getting MgCl2. Another process, 9.50 gram of sample of anhydrous magnesium chloride. So now it is as if reverse reaction, we are doing electrolysis of this compound, we are getting chlorine. So you can consider as if it is reverse reaction, but ultimately it is conversion of chlorine to MgCl2 or MgCl2 to chlorine. Fine. So MgCl2 we are getting in the first reaction from Mg and chlorine, and in the second case we are doing electrolysis of this compound. Okay. Now when we are doing electrolysis, then 2.24 liter of chlorine gas, as it is gas, the volume is 2.24 liter. So this is 2.24 liter. We are getting at NT. We have to show here that these data that are given in the question, they agree with the law of constant proportion, which is another name of definite proportion. So this problem is on the law of definite proportion. First reaction, 0.36 gram of magnesium, it is combining with chlorine, and we are getting 1.425 gram of magnesium chloride. So if we subtract 0.36 from 1.425, you can get the mass of chlorine. In this case, we can know the value of, that is the mass for all the reactants as well as products. Now in the second case, 9.50 gram of this sample we have taken, and we are doing electrolysis, we are getting 2.24 liters. So these are the informations that are given. So for the first reaction, here we can do the calculation. We have to subtract this if we want to know what is the mass of chlorine. Okay, so this is the mass of chlorine. Now we can say that 1.425 gram of magnesium chloride, this is actually producing this gram of chlorine if you consider the reverse reaction, because for the second case it is actually the reverse reaction. Actually, it doesn't matter whether you say that 1.065 gram of chlorine is producing 1.45 gram of MgCl2, or if you are saying the reverse statement, that is 1.42 gram of MgCl2 produces 1.065 gram of chlorine. So if this is the case, so from this we can easily understand, then 1 gram of magnesium chloride will be producing, simply divide this 1.065 by the mass of MgCl2. So this is the amount of chlorine that will be produced if the value of mass of MgCl2 is 1 gram. Okay, so now we know. So this is the value which we have to fix. Now for the second case, it is 9.50 gram of MgCl2. So for the second case, now 9.5 gram of MgCl2, we are getting 2.24 liter. But we have to fix this mass to 1 gram, because if we want to prove that it is obeying law of definite proportion, we have to fix this amount. So it is 1 gram, first reaction, second reaction also it is 1 gram. So when it is 1 gram, now this value should be multiplied by 9.5. So this is 9.5. And we are getting the amount of chlorine, but not in terms of gram. Now it is in terms of volume. But that doesn't matter. You can easily convert volume to gram. Fine. Now, though this information we have not discussed yet, but in this chapter only you will get to know that 2.24 liter at NTP condition, it always means that the corresponding mass of the gas will be molar mass of that particular gas. Now chlorine, if we consider its molar mass, it is 35.5 multiplied by 2, which is 71 grams. So this is the molar mass of chlorine. So molar mass will always have the volume 22.4. So if 22.4 liter is having mass 71, because the condition is NTP, that is given in the question. So for 22.4 liter, the corresponding mass is gram, but we want to know what is the mass for 0.236 liter of chlorine. So that is why 71 is divided by 22.4 and then it is multiplied by 0.234, and this is the mass of chlorine which you are getting from 1 gram of MgCl2. So these two values, if you consider, just compare these two, these are actually same value, right? So it means when one amount you have fixed, that means this is 1 gram, here also this is 1 gram, so the corresponding amount of chlorine, it is same for both cases. So that is why we can say that these data agree with the law of constant proportion, or you can say definite proportion. Next law, law of multiple proportion. When two elements A and B combine to form two or more than two different compounds, under that condition, the different masses of A, which separately combines with a fixed mass of B, that different mass of A for the first compound and for the second compound, if we are considering only two compounds, this ratio will always be whole number. So we will take particular example. So here only two elements are in, and these two elements are reacting with each other, but they can form different types of compounds. It may be two or more than two, but at least two is required, otherwise how we will compare? So when they are reacting and they are producing different types of compounds, just choose any one element and fix the mass of this particular element. Now for this fixed mass of that particular element, not necessarily it has to be B, you can also do it for A. So for that particular fixed mass of element, the second element, now it is reacting with that fixed mass in two different compounds or three different compounds. All this mass ratio will be in whole number ratio. We know that carbon can form oxide with oxygen. One is carbon monoxide. These two are very common. Another one is carbon dioxide. Now when it is carbon monoxide, here atomic mass of carbon is 12 and for oxygen it is 60, right? So 12 gram of carbon is reacting with 16 gram of oxygen. That means when it is 1 gram of carbon, it must be reacting with 16 divided by 12. So 16 divided by 12 is basically this value. So 1 gram of carbon reacts with 1.333 gram of oxygen. Similarly, when it is CO2, here 12 gram of CO2 is reacting with O2. That means now it is 16 into 2, 32. So if that is the case, so 12 gram of carbon reacting with 32 gram of oxygen. So 1 gram of carbon will react with 32 divided by 12, and it will be this value, 2.666. So 1 gram of carbon, when it is reacting with 1.33 gram oxygen, we are getting the compound CO, and when it is reacting with 2.666 gram of oxygen, we are getting another oxide, which is CO2. Now this is fixed mass. So here in the box what is written, fixed mass of B. So suppose here carbon is B. So if carbon is B, then oxygen is A. So fixed mass of carbon or the element B, now it is reacting with 1.33 gram of oxygen in first case and 2.666 gram of oxygen in the second case. So take the ratio of these two values. So it is 1:2. So it is a whole number ratio. So this is law of multiple proportion. Another example, nitrogen reacting with oxygen, and it can produce different types of oxide. So see the formulas. This is NO, 1 nitrogen atom, 1 oxygen atom. This is NO2. Now it is 1 nitrogen, 2 oxygen. So these are the different formulas. So 5 different compounds. Here you can see all these are oxides of nitrogen, but atomic ratio is different. So now what we will do, we will fix any one of these element. Now you can choose nitrogen or you can choose oxygen. We have chosen here nitrogen. So the mass of nitrogen we will fix it. But before that, let's see, according to this formula, here 14 gram of nitrogen reacting with 16 gram of oxygen. That means 1 gram nitrogen should react with 16 divided by 14. So now I can write as if it is 1:1.14. In this way also I can write. So here we have fixed the mass of nitrogen to the value 1. For NO2, when it is according to the formula, it is 14 gram of nitrogen reacting with 32. So 1 gram of nitrogen will react with 32 divided by 14. So the ratio is 1:2.29. Similarly for the third one, now 28 gram of nitrogen reacting with 16. So 1 gram of nitrogen will react with 16 divided by 28. So now it is fraction because 28 is greater than 16. Fourth case, again 28:48. So 28 gram reacting with 48 gram of oxygen. So 1 gram will react with 48 divided by 28, which is 1.71. Similarly, it is 1:2.86. Now, as you can see all these ratios, 1:1.14, 1:2.29. What we will do next? In the next step, we will divide all this ratio. So I am now erasing it for simplicity. So just focus on this value, which is for oxygen. And here, among these 5 values, this is minimum, right? So we will choose this one and divide all these 5 values with 0.571. So when you are dividing 0.571 with 0.571, it will be 1. When you are dividing 1.14 with 0.571, because you are dividing all these values with 0.57, so that we can get this type of whole number ratio, 2:4:1:3:5. So if this is the ratio of oxygen, so as if here A is oxygen and B is nitrogen. So we have fixed the mass of nitrogen. So according to this line, what it says, separately combines with a fixed mass of B. So here oxygen mass is different and the mass of nitrogen we have fixed. So as you can see, it is a whole number issue. Okay. So the first example, only 2 compounds, because minimum 2 compounds must be there, otherwise how we will compare. But it may be more than 2. Here you can see it is total 5 compounds. Okay. Problem on law of multiple proportion. So this law that we have just discussed, now we'll see this problem. The law of multiple proportion is illustrated by the pair of compounds. Here we have compound sodium chloride, sodium bromide, NaBr, NaCl. Sorry, I have written NaBr first, but it doesn't matter. Here, these are the formula. Then water and heavy water. That means this is the formula of water. This is heavy water, right? Then sulfur dioxide. So this is the formula. And trioxide. This is the formula. Then magnesium hydroxide. Formula is MgOH2. Then magnesium oxide. Okay. So now we have written all the formulas for all the options. Law of multiple proportion. What we have seen? There are actually 2 elements, right? And they are forming different types of compounds. So suppose one element is X, another one is Y. So they will form compound to each other. So there should not be any third element. But if you look at option 1, there are total 3 elements involved. So this is not possible. Then option B. Here it is true that both are water, but here isotopes are involved. So for isotope we cannot apply this. Then we have sulfur dioxide and sulfur trioxide. So now you can consider as if here X is S and Y is oxygen. So in the first case SO2, that means the formula is XY2 or it may be XY3. So now it is only 2 elements that are involved, sulfur and oxygen. So this should be the correct option. Okay. And the last one, obviously it is not true, because in the first case magnesium, oxygen, hydrogen, total 3 elements together is making magnesium hydroxide, but in the second case only 2 elements are present. So here 3 elements, here only 2 elements. So this is not at all possible. So third option is the correct option. Now if we that is want to go into details, in SO2, just consider its atomic mass. 32 gram of sulfur is reacting with 32 gram of oxygen. So atomic mass of sulfur is 32, but for oxygen it is 16, but 2 oxygen atoms, so 16 into 2. So we can write this statement: 32 gram of sulfur reacting with 32 gram of oxygen. For the second oxide of sulfur, now this is also 32, but this one will be 48, because 3 into 16 is 48. So now 32 gram is reacting with 48 gram of oxygen. So this is already fixed. Under that condition, these two, we should take the ratio, and this is the ratio, simple whole number ratio. Okay. Carbon is found to form 2 different oxides that we have just seen. One is carbon monoxide, another one is CO2, which contain 42.9% of carbon, 27.3% of carbon respectively, because 2 oxides are there. Show that these figures illustrate the law of multiple proportion. So once you know the percentage of carbon, obviously by subtracting from 100 you can get the percentage of oxygen. So this table you can see the first oxide, this is the amount of carbon given. So if you subtract 42.9 from 100, you will get this one. When you subtract for the second oxide, the percentage of carbon, which is already given in the question, from 100 you will get 72.7%. So these are the percentage. Now we have to fix any one of these. So you can do a fix you can choose any element, it's up to you. So here I am writing 72.6 gram of, though it is in percentage, but I can write gram. It is reacting with 27.3 gram of, sorry, it will be carbon. So 72.7 gram. So this is I am writing for the second oxide. Look at this second column, 72.7 gram of oxygen. It is reacting with 27.3 gram of carbon. Next, what we'll do, we will find out if it is so, then for 57.1 gram oxygen, the corresponding amount of carbon should be, calculation will be like this. So this is the mass of carbon. If the mass of oxygen is 57.1 and this value is 21.44. If it is 21.44, now in the first oxide 57.1 gram oxygen, it is reacting with this value of carbon. In the second oxide, again 57.1 gram of oxide, it is reacting with this amount of carbon. So we have to take the ratio of 42.9 divided by 21.4, and if you do this you will find it 2.005 something is to 1. So this is the ratio, which is nothing but 2:1. Okay, so in this way we can prove that these figures are illustrating the law of multiple proportion. After this, the next law, reciprocal proportion. Now 3 elements will be involved. So in this case we will take 3 elements, x, y and z. 2 elements, suppose x and y, they are combining separately with the same weight of a third element, and that third element is z. So x is reacting with a fixed mass of z. Y is also reacting with a fixed mass of z. Now the ratio in which they are doing so, that means X and Y, that ratio will be same or simple multiple of the ratio in which they are combining with each other. Read it carefully. It is to some extent complex than the previous laws that we have discussed. But with proper example, it will be clear. Again, I am saying two elements X and Y, they are combining separately with a fixed mass of a third element. So X is reacting with Z, then Y is also reacting with Z. Fine. And they are forming two different compounds. Suppose XZ, YZ. Now it is also possible that X and Y, they are reacting with each other and they are forming, suppose XY. So that is another compound. Okay. Now the mass of Z is fixed. X is reacting with Z, there will be some mass. Then Y is reacting with Z, there will be some mass. So that to mass, there will be some ratio. So suppose this is ratio number 1. I am writing R1. Now when X and Y, they are reacting with each other, forget about Z. Now there is no picture of Z, is not in picture. Now X and Y reacting with each other, and now the ratio is suppose R2. So these two ratio, they will be either same or multiple of the ratio. Okay. So now see, three elements here we have: carbon, hydrogen, oxygen. So carbon can react with hydrogen, it can form compound methane. Carbon reacting with oxygen, it is forming compound CO2. And hydrogen and oxygen, they are reacting with each other, they are forming water. Now we have taken these two compounds only. Among these three compounds, we have taken methane and CO2. So in both cases, which one is common? Here common is carbon. So combining elements C and H in the first case, C and O in the second case. So here C is fixed. So suppose this is Z, because we have fixed it. This is Y X, this is Y. So Z is fixed. Okay. And if you look at the formula CH4, the corresponding mass of carbon, because only one carbon atom is there. So atomic mass 12. 4 hydrogen means total mass will be 4. Similarly, from the second formula CO2, it is, I can say as if it is ZY. I'm just analog, I am writing XZ, and H2O will be XY. So here from the formula CO2, 12 gram of carbon, it is reacting with 32 gram of oxygen. So the mass of carbon is already fixed. And if you now take the ratio 4 and 32, it is 1:8. Now consider the formula of H2O. What is the mass of hydrogen? 2 from this formula. And what is the mass of oxygen? 16. So again you are getting the ratio 1:8. So this is suppose ratio 1. This is ratio 2. So these two ratios are same. Though I am saying not necessarily they has to be same. It can be multiple also. So suppose in first case it is 1:16. In the second case 1:8. Then also the law is okay. So in this case it is same. Fine, there is no problem. Another example. Copper reacting with sulfur. This is the formula CuS. These are the mass given. Only one atom is involved. So this is the atomic mass. Now copper is also reacting with oxygen. So here Z is copper. X and Y, sulfur and oxygen. Again, the masses are given. And sulfur, when there is no copper, it is now reacting with directly with oxygen. So both are 32, 32. Oxygen is actually 16, but 2 oxygen atoms, so it will be 32. So in the first case, the mass of copper is fixed. Now if I take the ratio of sulfur and oxygen, it will be 32 and 16. That means it is 2:1. In the second case, if you take the ratio, it will be 1:1. So now they are not same, but that doesn't matter because it is already mentioned that it may be same or simple multiple of the ratio in which they are combined with each other. So here the first ratio is twice the second ratio, right? So second ratio is 1:1. So RSO, first ratio, R prime SO, that is the second ratio. So if you multiply actually the second ratio, yes, the first ratio, which is 2:1, as if it is double of this. If you multiply, that is only one value is multiplied. Don't think that the both of these are multiplying. So either same or simple multiple of the ratio, not fraction, simple multiple. Okay, so this is law of reciprocal proportion. Problem related to this. Here we have some compounds given in options A, B, C, D. Which among the following combinations illustrate law of reciprocal proportion? In all the four options, total three compounds are given. Okay, so in the first one, there are some oxides of nitrogen. So only two elements are present, right? As if it is X and Y. In the second case, sodium chloride, bromide, and iodide. That means sodium is fixed. And how many elements are there except sodium? Total 3. That means total number of elements 4. So obviously these two, as you can, we just discussed reciprocal. There we have seen there are total 3 elements involved. But in the first option, only 2 elements. Here, total 4 elements are involved. So we cannot apply reciprocal proportion. Okay. Then option C. Here H2O, H2S and SO2. So suppose if I am writing XYZ. So H, suppose this is H, this is oxygen, this is sulfur. So H2O is basically XY, H2S is basically XZ and SO2 is basically YZ. So now you can see total 3 elements are involved. Not just 3 elements, that is not enough. 3 elements and also they are having compounds like this. That is all the combinations possible. XY, YZ, ZX. If I am saying it is ABC, it will be AB, BC, CA. So these should be the correct option. But if you consider option D, now again see 3 elements are present X, Y, Z. So suppose one is phosphorus, another one is hydrogen, then oxygen. The first compound is pH3, that means it is XY combination of X and Y. Second compound P2O3. So it is combination of PO, that means it is XZ. Now the third compound, that is also XZ, isn't it? Though atomic ratio is different, but it is also compound of X and Z. So here also 3 elements are present. But remember, mere presence of 3 elements, that is not necessarily criteria. 3 elements must be present and also it should be like this, as you are seeing in option C. That is the compound should be all the permutation combination XY, YZ and ZX. So option 3 is the correct option. So after these 4 laws, now the next 2 laws that are basically related to volume. Fine. So here it is saying at a particular temperature and pressure, not just any temperature pressure, a particular temperature pressure, the volume of all gaseous reactants and products. So the reaction that will be involved here, reactant should be gaseous, product should be gaseous. What we can say under this condition, volume of all these gaseous reactant products, they will remain in simple whole number ratio to each other. Example we have taken, nitrogen is reacting with hydrogen. It is producing ammonia. And if you look at the equation carefully, it is balanced. 2 nitrogen atom, 3 H2, that means 6 hydrogen atom. If you look at the right hand side, 2 nitrogen and 2 into 3, 6 hydrogen. So it is balanced. So when it is, I am saying that as it is gaseous and nitrogen, it is one volume Here coefficient is 3, so 3 volume, and here coefficient is 2, so it is 2 volume. So the ratio of this volume is 1:3:2. Okay, so that is according to Gay-Lussac's law of gaseous volume. Now if I write it in this way, see here how here this individual, these pictures, it means it is nitrogen because it is diatomic. So total how many nitrogen molecules are present? Total 4. 1, 2, 3, 4. Next, if you see hydrogen gas, which is again diatomic, how many are there? 3, 4. 4 into total 3 boxes are there. So 4 into 3, it is 12. And how many ammonia gas molecules are there? It is triatomic. 1, 2, 3, 4, 5, 6, 7, 8. So total 8. So here the ratio is 1:3:2. Now if you simplify this ratio, 4:12:8. 4, 12, 8. So if you simplify it, just divide with the smallest number. Smallest number is 4. So it will be 1, 2. So see, it is same. So in the first case, from the balanced equation, you have already seen it is 1:3:2. Now when we have written it in this way, then also we are getting same. Fine. So in this way, we can understand that this picture illustrates Gay-Lussac's law of gaseous volume. Related problem. 40 ml of methane. Methane is formula, having formula CH4. Completely burnt using 80 ml oxygen at room temperature. Remember here this is important, at room temperature. Now there will be some product formation. The second line is saying the volume of the gas left after cooling to room temperature. Now reactant side, there is presence of oxygen and methane, and they have completely reacted with each other, so nothing is left. Now in the product side, what will be the products? Products will be combustion product because it is combustion reaction. Hydrocarbon reacting with oxygen. In hydrocarbon there is carbon and hydrogen. Carbon reacts with oxygen, it will produce CO2. Hydrogen reacts with oxygen, it will produce water. So products are basically CO2 and water. But remember, the second statement is saying volume of gas left after cooling to room temperature. Now when you are cooling the reaction to room temperature, water which is produced as product, it will be converted to liquid, because at room temperature water cannot remain in vapor condition, right? 25 degrees centigrade, it will remain in liquid form. So now you cannot consider volume because as it is not in the gaseous physical state, it is now in liquid physical state, so we cannot consider this. So look at this equation. Methane is reacting with oxygen, we are getting CO2 and H2. You can easily balance this equation, it is very easy. As the formula of methane is CH4, that means only one carbon. So from one carbon you can get one CO2, because atom must be maintained, number of atoms of carbon. Similarly, when it is 4 hydrogen in the formula of CH4, so in the product side also 4 hydrogen must be there. So the formula of H2O, that is the coefficient before the formula, it will be 2. Then only it will be 4 hydrogen. So CO2 is one molecule, here 2 molecules of water. So how many molecules of, that is in terms of atoms, how many atoms of oxygen? 2 oxygen, 2 oxygen. So it is 4 oxygen. So that is why we have added 2 in the left hand side. So this is a balanced equation, right? So if starting amount of it is 40, then as it will always maintain whole number ratio according to Gay-Lussac's law of gaseous volume. So from 40 ml methane, you can get maximum 40 ml of CO2, and here we have coefficient 2, so it will get, you will get 80 ml of 80 ml of water, but when it is in vapor form. Remember, You can write it only when it is in gaseous form. Then only it is true, but it is already at room temperature. Fine. So first option, it is saying only 40 ml CO2. Then the second option, 40 ml CO2, 80 ml H2O. Now option B, at a first glance, it seems it is correct, but it is correct only when it is possible if this part is not mentioned in the question, but it is already mentioned in the question. So option B, though at a first glance it seems true, but it is not true. Okay, correct answer will be 40 ml CO2 because it is already converted to liquid form. So we have to consider only gas. So that is why correct option cannot be option B, it is A. So in this table you can see stoichiometric ratio, that is the coefficient. If you consider, it is 1:2:1. We have written only these three because though here total 4 compounds involved, before reaction 2 compounds, after reaction 2 compounds, but we have written only 3 because we have to consider room temperature, and at room temperature only these 3 compounds can remain in gaseous form, not water. So water is not written in the table. So volume of reactants allowed to react, because when it is 40, obviously oxygen, because of its coefficient 2, it will be 80. And volume of reactant reacted and product formed. This only product CO2 we have to consider. So that is why this should be the correct option, not second one. So we should always read question very carefully, because if it will be option B, then it will be very flat answer. But mostly we'll see questions, there will be something different. So it is not so straight cut, right? Calculate the volume of oxygen required at condition STP for the complete combustion of 5 dm cube of ethane. So this is the volume unit, cubic decimeter. Temperature given 295 Kelvin. Pressure is also given, but it is in different order, not atmosphere or millimeter, because there may be different types of units. So here the unit is N per meter square. Okay. So complete combustion of ethane. So ethane is having formula C2, sorry, H6, right? This is the formula of ethane, and it is reacting with oxygen. We know combustion product CO2 and H2O. Now in the left hand side 2 carbon, that means this should be 2. In the left hand side 6 hydrogen, that means this should be 3. Now it is total how many atoms of oxygen? 4 here, 3 here. So it is 7 oxygen atom. So it must be like this, 7 by 2, right? Now here 5 dm cube, that is the volume of ethane. So if it is 5 dm cube volume of ethane, then the corresponding volume of oxygen, that you can easily find. So when it is 1, then the corresponding amount is 7 by 2. So when it is 5, then the corresponding amount should be 5 into 7 by 2, which is 35.2, or we can say it is 17.5 dm cube. So in this way, you can find that the amount of oxygen that is required for reaction of 5 dm cube of ethane at this condition, because temperature and pressure is given. So now we know what is the volume of oxygen required for reaction with 5 dm cube of ethane, but this value is only for 295 Kelvin and 0.993 10 to the power 5 N per meter square pressure under this condition. But we have to find the volume of oxygen for STP condition. So next thing is, so this first part is actually related to Gay-Lussac's law. The second part is related to gas chapter. Fine. So here the pressure that is given, this is P. Temperature that is given, this is capital T, and this is the volume that we have just calculated. but we have to find the volume which is V naught, but this V naught is under P naught and T naught temperature. Now T naught STP condition means 273 Kelvin or 0 degree centigrade, and in terms of pressure, this is the value for pressure when it is STP condition. So now we will apply the formula, that is remember what we know is PV divided by T, that is equal to P naught V naught T naught. So here only V naught is unknown, rest of the all these quantities we know, right? So we can easily find it. Here we have to put the values of P, V, T, T naught and P naught. So this is P, this is V, this is T naught. This one is T, that is the initial temperature, and this is P naught. So in this way, if you calculate, you will see it is 15.88 dm3. You don't have to change the unit of volume because both side it will be cancelled. It doesn't matter anything which value of volume is present. Okay, so this is the answer. This is the volume of oxygen that will be required when it is STP condition. If it is not STP condition, suppose if it is 295 Kelvin and this pressure, then the amount of oxygen required is 17.5 dm3. But when the condition is different, STP, now the amount of oxygen is also different. Now it is reduced to 15.88. So after this, there is one more law which is Avogadro's law. But if we do not have the idea of the concept of mole, we cannot understand that law. So that is why we should know first what is a mole concept. We all know that atoms and molecules, they are extremely small in size. And when something is very small in size, obviously their numbers in even a very small amount. If you consider any substance, suppose I am saying that there is a presence of, in any particular container, there is presence of oxygen gas. Now, if I say what is the number of atoms and molecules, as their size is very small, so obviously the number will be very high. Even if the amount of that particular oxygen gas is very low, then also the number of these particles, because of their small size, that will be very high. So that is why handling these large numbers, it is really difficult, right? So that is why we need a unit which will be for day-to-day life, that will be, we can easily handle it, convenient. So that is the purpose, that is the concept of mole is required. Now simply take, we know that dozen means when we represent any quantity which is in the number 12. So if I say it is 12 roses, sorry, if I say it is 1 dozen roses, it always means 12 roses. 1 dozen balls, 12 balls, 1 dozen apples, 12 apples, right? So here 12 numbers, it is equal to dozen. That means if I am saying we have 144 roses. Now 144 roses, if you simply divide it by 12, it is actually 12 dozen roses, because 12 into 12 is 145. That means now when I am saying 144 roses, that is one thing, or I am saying 12 dozen roses, both are actually same thing. But when you, now in the second case, you are handling, that is the same thing, but now you are expressing it with a small number, which is easier to handle. So that is the reason now we will use the term mole. We represent, that is when we say mole, it means this number of any quantities, not necessarily it has to be atoms or molecules. Suppose if I am saying 1 mole ion, then also it will mean that 6.022 into 10 to the power 23 number of ions are present, or number of electrons are present, or number of protons are present. So any particle which is very small inside, it may be atom, molecule, ion, electron, proton, neutron, anything. but particle size is very small. That means their quantities are very high. So now whenever you are getting any quantity, simply divide it by this number, you will get the number of moles. So when we express it in terms of moles, it will be easier to handle. Mole is the SI unit to represent a specific amount. Just we represent anything in number 12 with dozen. So 1 mole contains exactly this number. Here also the number is given, but it is only up to decimal 3. But if you really want to know in detail, this is the value. But remembering up to this is enough. 6.022 or 023. Mostly we use into 10 to the power 23. So this number of any elementary entities are present: electron, proton, neutron. Now this number is the fixed numerical value of Avogadro constant. So this number is expressed like this: n subscript a, or you can say it is a Avogadro constant because it is a fixed value. And sometimes what we do, if you express it with this unit, that is mole inverse. Suppose I am saying this is the number present per mole. So that is why the unit will be now per mole. So when you are expressing this value in terms of number, then you can say Avogadro number rather than saying Avogadro constant. So when you are saying it is number, it will be per mole. But if you are saying it is constant, it will be simply the number without any unit. Fine. So this is the concept of mole. Now we will apply this concept to the next law. Avogadro law. It is saying that equal volume of gases at same temperature and pressure should contain equal number of molecules. So suppose we have taken this particular portion in this balloon. So in each case the volume is fixed. So you can see when it is hydrogen molecule, how many hydrogen molecules are there? 1, 2, 3, 4, 5, 6, 7. In the second case also 1, 2, 3, 4, 5, 6, 7. In the last case also carbon dioxide, which is triatomic. You can see 1, 2, 3, 4, 5, 6. So when you have taken fixed volume, the number of molecules will be same. Okay, or number of, if it is monoatomic, number of atoms will be same. Now if I am saying the volume is 22.4 liter, and remember it is only at STP condition applicable. Okay, so when I am saying the statement of this law, it is mentioned same temperature and pressure. This is fine. But when I am considering this particular value 22.4, remember it is only applicable at STP condition. So under STP condition, if the volume is 22.4 liter, any gas, it doesn't matter which gas you have taken, any gas, it will always be having Avogadro number of that particular molecules. Now we know Avogadro number, it is actually 1 mole. So that is why here it is directly written 1 mole. So 22.4 liter of any gas, if the condition is STP, it will be always containing that number, which is the number of 1 mole, and 1 mole is nothing but 6.023 10 to the power 23, right? So as the law says that volume and amount of the gas, you can consider as if it is number of moles of the gas, they are directly proportional to each other, right? So if here we have taken this fixed volume, suppose if you double the volume, it will be, instead of 7 molecules, now there will be 14 molecules, 7 into 2 for these two also. So in this way, now as it is directly proportional, that is the volume and amount of gas, the statement we can express mathematically in this way. So now I can say that volume that is proportional to n. So n is nothing but number of moles. Okay, so if it is so, now if you remove this proportionality sign, you can fix some constant and then it will be into n. Okay, so when this type of proportionality is present, now you can also write, suppose if it is V1 that is proportional to N1 number of moles, suppose another volume is V2 proportional to N2. So under this condition, we can say that V1 by N1, that will be equal to V2 by N. Okay. So this ratio is always constant. Okay. So that means it is directly proportional. So problem on this law. 3 balloons are present. They are filled with same gas but different amount. One balloon is filled with 3 moles of the ideal gas and the corresponding volume is 30 liter. Another balloon which is containing 2 moles of gas, you have to find the corresponding volume. And the second question is, there is another balloon which is having volume 45. You have to find moles. So these two questions, they are reverse. See, up in the first question, that is A question, mole number given, you have to find volume. Second question, volume is given, you have to find mole. And in the question already this information is given, that how many moles and what is the corresponding volume. Now if we represent it in this picture as if this is the balloon where both the values are given, 3, 30, that means number of moles, number liter. So here if I am writing, it is N2, so N2 V2 both are given. Now in the first case, here only N1 is given, but V1 we do not know. In the third case, N3, that we do not know, but V3 we know, right? Now if it is the case, as we have already mentioned, that we can write this N1 V1, you can also write V1 N1, it doesn't matter anything. Okay, better and write it. So here only the middle one, that value is known. So V2 by N2, V2 by N2 is 30 divided by 3, which is basically 10. Now V1 and N1, you know only N1. So if N1 is 2, that means V1 divided by 2, 10. In the third case, we know V3, 45, but we do not know N3, but we know the ratio. So in this case, you can easily find it. V1 will be 2 into 10. So the first answer will be, the volume is 20 liter. And in the last case, the number of moles, how many moles? It will be 45. That should be divided by 10. So it will be 4.5. So the second answer is 4.5 and the first answer is 20. Okay. Dalton's atomic theory. So here, though we are starting it, and there is also limitations of this. Fine. So we'll not be able to finish, but still we'll see some idea. This theory, so all the laws are discussed. Now this theory is saying, though it is based on laws of chemical combinations, but after discussing it, you would also see there are many limitations also. So the basic postulates are, all substances are made up of tiny indivisible particles called atoms. So further you cannot have any small particle. This is the last small particle possible. All the atoms of a given element. That means if the element is fixed, suppose you have only oxygen, there is no other element. So if it is only oxygen, then obviously all the atoms of oxygen, they will have identical mass. Third one, if it is different element, suppose you have oxygen, one element, second element nitrogen. Now the atoms will be different in mass. Fourth one, compounds are formed when atoms of different elements combine in a fixed whole number ratio. So if there are suppose 2 elements or 3 elements, they are combining with each other, this combining ratio, atomic ratio, that will always be whole number. Then the next one, chemical reactions involve reorganization of atoms. So suppose you are reacting nitrogen with oxygen. There is one arrangement of the atoms individually for oxygen. There is another arrangement for atoms of nitrogen in the other element. But when they are forming compound and there will be nitrogen oxide, different types of nitrogen oxides are there, atoms will be reorganized. These are neither created, that is, atoms are neither created nor destroyed in a chemical reaction. Fine. So these are the postulates, but there are limitations. So Dalton's atomic theory, just consider here we are producing water molecule. So starting material is oxygen and hydrogen. If you look at the formula of water, it is 1 oxygen atom, 2 hydrogen, and mass is 18. So we should start from 2 hydrogen atom and 1 oxygen atom, right? These two will combine together, it will make H2. So in this picture, in the first picture, you will not see an involvement of electron, because according to Dalton, atom is the last small particle possible. Further division is not possible, it is indivisible. But actually, modern atomic model, it says that there are actually presence of proton, neutron, electron. Atom is not the indivisible particle, it is not the last small particle possible. So that is why now you can see in oxygen, there are total 8 electrons present. So that is already given in this picture. Similarly, if you consider hydrogen, there is only 1 electron. So these 8 electrons in oxygen and one electron in these 2 hydrogen atom. Now there is rearrangement in the electron, not reorganization of atom. So this is according to modern atomic model, which is not matching with Dalton's atomic theory. So obviously this is limitation. So details of these limitations, point by point, we will discuss in the next class. And we'll end here. Thank you for listening.